I am Amanda. Hi, I'm Samantha. Hi, I'm Alexis. Hi, I'm Mama. Welcome to another episode of
Clean Code.
Clean Code. Your best episode of this. In this episode by Uncle Bob. Uncle Bob. Enjoy. Uncle
Welcome to Clean Code, episode 16, Component Cohesion. Come on in. Let me take your hat. So, this episode is the second in our series on components. And in it, we're going to be learning about the 3 principles of component cohesion. Come with me. Remember, last episode, we studied the coffee maker example. And remember how we used the solid principles to put together a set of components that behaved well enough to drive a coffee maker? Those components were defined by boundaries, and all the dependencies that crossed those boundaries crossed, pointing in one direction in accordance with the dependency inversion principle. The components could be jar files, DLLs, shared libraries. It doesn't matter about their form. They're all relocatable libraries, and they're dynamically loadable. What's interesting about them is that they hold all kinds of code. They hold subroutine code, framework code, application code. It really doesn't matter, except for one thing. There's one overriding rule, and that rule is that high-level policy should be kept ignorant of low-level detail. The components that contain details depend on the components that contain policy. So now in this episode, we're going to study the 3 principles of component cohesion. The release-reuse equivalence principle, the common closure principle, and the common reuse principle. But before we do that, we're going to dive into why white dwarf stars blow up into type 1a supernova. And then I want you to grab your iron picks, because we're going to dig deep into the principles of component cohesion. Last time we talked about how the sun, at the end of its life, will become a white dwarf star, an object made of carbon that resists its own gravity through the pressure of electron degeneracy. Remember all that stuff about the Pauli exclusion principle? So does that pressure have a limit? I mean, how much weight can electron degeneracy hold? Remember that the pressure of electron degeneracy is based upon the speed of the electrons as they fill the available energy levels. Remember also that nothing can move faster than the speed of light. And since energy is quantized, meaning it cannot be infinitely subdivided, there must be a final energy level that the electrons can fill before they would have to move faster than the speed of light. And it is this level that defines the pressure limit of electron degeneracy. That limit was discovered on the Orient Express in the year 1930 at the ripe old age of 20. A young fellow by the name of Subraman Chandrasekhar solved the formulas of general relativity that described the electron degeneracy pressure at the core of a white dwarf star. And he showed that that electron gas could only support a pressure equivalent to 1.44 times the mass of the sun. Indeed, Chandrasekhar won the Nobel Prize for this accomplishment. Since that time, this limit has been known as the Chandrasekhar limit. Stars often come in pairs, and sometimes those pairs can be pretty close to each other. So what would happen if a white dwarf star had a really close companion and it gradually stole mass from it? The mass of the white dwarf star would increase towards the Chandrasekhar limit. The infalling atoms would all enter the degenerate state, and the temperature would increase because the new electrons would be forced into higher and higher energy levels, moving faster and faster. And then, just before the Chandrasekhar limit was reached, the carbon atoms in the white dwarf star would begin to fuse into neon, magnesium, and sodium. This fusion releases a lot of extra heat, and in a normal gas, that heat would cause it to expand and thereby cool down. But this is a gas of degenerate electrons, and degenerate electrons don't expand when they get hotter. So the increase in heat causes the temperature to skyrocket. The increase in temperature greatly accelerates the speed at which the fusion reactions take place, therefore causing all of the carbon within the white dwarf star to fuse within a few seconds. The resultant output of energy is many billion times greater than a normal star, and is sufficient to blow the white dwarf star apart at 6% the speed of light. Needless to say, this is a pretty big explosion. It's called a Type 1a supernova, and we don't want to be close to one. 50 light years would be a bit too close. Inside of 50 light years, we'd get a significant dose of gamma and X-rays, and that radiation would deplete our ozone layer. These events last for several weeks, and so the Earth would be broiled like a chicken on a rotisserie. Now, there ain't no point in letting the horses all run loose out of the barn, because there's no white dwarf stars anywhere near us that can do us any harm. These events are impossibly rare. In fact, you'd be lucky to see one within 100,000 light years in your whole life. Indeed, in any given galaxy, you'll hardly get more than one per century. We haven't had one visible in our century for over 400 years. But if we did, and if it was within a couple of thousand light years, well, then it would be one heck of a show, because it would be visible during the day and you could read by the sucker at night. Correct me if I'm wrong, Spock, but aren't these events all very similar? Indeed, Captain. Since every Type 1a supernova is caused by a white dwarf star that encroaches upon the Chandrasekhar limit of 1.44 solar masses, they all erupt in a similar fashion, they all have similar power outputs, and follow similar light curves. And because they're all about the same brightness, we can tell how far away they are quite precisely. We have used this information to calculate the acceleration of the expansion of the universe. Cool. Consider for a moment the peculiar fact that we live inside a runaway expanding universe, adorned with Earth-sized diamonds that weigh more than the sun, that from time to time blow themselves to hell and gone. We truly all do live in the Twilight Zone. In the last episode, we learned that components are binary deliverables. They take the form of dynamically linked libraries, DLLs, jar files, gem files, or shared libraries. Whatever their form, what defines them as components is that they are ready to run. They are deployable as part of a running system. But what's inside a component? What are the pieces that it's made of? And what are the forces that bind those pieces together into an independently deployable unit? The pieces are functions. The forces that bind those functions together are called cohesion. Wait, functions? What about classes? Classes are just the first layer of cohesion for functions. Perhaps you find this confusing. Perhaps you think that classes are more about data than functions.
But this would be an incorrect view. The data defined by classes are unimportant details. The evidence for this is that we keep all this data private, invisible, hidden from the users. The only visible parts of a class are the public functions that give it purpose.
So classes are the first layer of cohesion for the functions in our program. Those functions that deal with a set of common data elements are grouped together into classes. But classes can be cohesive too. Sometimes they belong together, and sometimes they don't. It is this force of class cohesion that we will use to define our components. In the search for the forces that bind classes into components, we are constantly bedeviled by the contrary forces of false cohesion. Programmers often get confused about which classes belong in a component and which don't. The most common problem is a subsystem error. The fact that a group of classes work together to achieve a certain goal is not necessarily a good reason to bind them together into a single component. For example, the classes that calculate pay for different types of employees probably ought to be kept in separate components. The class that formats a report does not belong in the same component with those classes that calculate the values displayed within that report. It is unlikely that the classes that query the data should be combined together in the same component with the classes that use the queried data.
In short, bucko, you don't go putting classes together into a component just 'cause it feels right. Feeling ain't got nothing to do with it. You gotta have a real reason to put them classes together. And that reason's gotta be better than just some itch in your shorts.
Another common error that developers make is to bundle whole inheritance hierarchies together into a single component.
Remember that dependencies are inverted across inheritance relationships. The flow of control opposes the source code dependency. And this is exactly what we want when we cross component boundaries.
And so base classes and their derivatives are often packaged into separate components, whereas those classes that use a base class are often packaged into the component with the base class.
Now there's no reason for you Ruby and Python programmers to get your panties all up in a bunch. When one class polymorphically uses another, those two classes should find themselves in different components.
There are many other forces of false cohesion that we could study. Suffice it to say that if you fall prey to these, your components are going to be too tightly coupled. You'll know that this has happened if you find that it's difficult to independently deploy them. The goal of a good component structure is to be able to change one component without having to redeploy any of the others. The goal is independent deployability.
Hey, buddy, you need a component?
Now let's say that I've got a component and I want you to use it.
It's cool, trust me, you'll want to use it.
So, what do you want from me? Clearly, I want the component itself delivered in a convenient package. No problem. I'll give it to you in a zip file. It would be important for me to have your test suite so that I could prove that your component worked within my environment. You got it. I got that test suite all bottled up and ready to run. It'll be on that zip file.
Documentation! I want documentation!
Yeah, I've got that too. I've got a great big PDF file loaded with all kinds of goodies. Describes all the functions, the whole design of everything. Remember, you also have those tests there. All this is going to be in the zip file.
Well, you're going to fix it, ain't you? I mean, if I find a bug, I don't want to be fixing it for you. I want you to jump on your horse and fix that sucker ASAP.
Absolutely. I'm going to be on top of it. If you report a bug, I'm going to have that bug fixed before you know it. I'm going to maintain this, not you.
I don't want you to change anything that I depend upon. I don't want to have to change all my code just because you change yours.
Yeah, well, about that. Look, I got lots of users. They're all going to be asking me for changes. I'm going to have to make those changes. I've got my own projects as well that I'm going to have to make changes for. So I can't really guarantee that those changes won't affect you.
I suggest you get those changes under control, or I may have to manedicate you.
Okay, look. What if I give you a warning in advance before I make these changes?
What good is that gonna do, son? I mean, what am I supposed to do with your warning? Feed it to my mule? I can't do anything about this until I get the concerned code. And by then, it's too late.
Okay, so what if you just try the new version and see if it works?
And what if it doesn't work? What are we supposed to do about that? Are you going to maintain your old version until we manage to make all our code work with your new changes?
Well, I can't just keep on maintaining all the old versions. So, what about this? What if I promise to maintain the previous release for a month or two, while you try to get your code working with the new release?
Yes, that would allow us to use the old version in production, while getting the new release ready with the new version. A logical approach. Now, wait just a cotton-picking minute there, Spock. I know you're supposed to be all logical and everything, but what am I supposed to do if I don't like that new version? What if I want to keep on using the old version that's not going to be maintained anymore? What am I supposed to do? Put it in a pot and cook it for dinner?
Okay, wait, hold on, guys. Look, if you don't like the new version, I'll let you fork the source code of the old version, and then you can continue to maintain your fork. After some time, I imagine you could accumulate quite a few different versions of your component. Some new, some old, and some forked. It would be easy to lose control of all these different versions, so I suggest you implement a version numbering technique and follow it rigorously. Yeah, Data, I think you're right. I mean, yikes. What have I gotten myself into?
And so it would appear that those hapless programmers who selflessly offer their software components to the world will find themselves rewarded with a lifetime of managing release cycles and version numbers. And that's the point behind the release-reuse equivalence principle. It says that the granule of reuse is the granule of release, which means that you can't reuse a component unless its author is willing to manage it through a release cycle. But managing release cycles is expensive. The more components a team has to manage, the more time they'll spend administering the release cycles, and the less time they'll have for writing code.
So the first rule of component cohesion is that a component needs to be large enough, it needs to have enough classes in it, to justify the cost of managing the release cycle. You'd rather manage a few strategic components than dozens or hundreds. So let's put this into real terms. A component is a DLL, a jar file, or a gem. You don't want your project saddled with hundreds of these. What you want is a few strategic components, not a plethora of little tiny ones. Hi, I'm Danny.net, and I'm the proud owner of a product that has a Visual Studio solution file with 567 projects in it. That means that we make 567 DLLs with a single build. Microsoft was so impressed by this, they didn't even think that Visual Studio could handle that many projects. So now they use my product build as one of their acceptance tests. Hi, I'm Jerry Duke Java, and my Java project has got packages galore, thousands of them. Some of them are sub-packages, some of them are sub-packages. And then when we build it into over 652 jar files. And then we take all those jar files and we wrap them up into one gigantic war file. Of course, we manage the whole thing with Maven. Man, you should see our pom.xml file. Or maybe you shouldn't. Hi, my name is Rodney. Rodney, I program in Ruby. You can call me Ruby Rod. And man, you should see our project. We've got 1,752 gems. Our gem file is just ginormous. It takes us a half an hour just to update all those gems. It's pretty hard to find things in that gem file. Let me tell you, we've lost like whole programmers in there. These aren't good outcomes. What we're after are projects that have a few strategic gems, jars, or DLLs, not a huge random pile. We want components that we can afford to manage, not a chaotic heap that we just dump into gem files, Maven scripts, or huge Visual Studio solutions. One way to avoid having that big, huge, random pile, that chaotic heap, is to remember that every component deserves to be managed by a release cycle. And that makes the component, the granule of reuse, also the granule of release. So the release-reuse equivalence principle tells us to manage our components using a release cycle. And that means we're going to figure out release numbers, we're going to have to do record keeping, date management, we're going to have to grandfather old versions. There's a lot of work involved with this. And all that work means that a component really can't be very small. It has to be large enough to justify the cost of managing releases. And that leads to an interesting question. What goes into a component? What are the partitioning rules? How do we know what classes to group together and what classes to keep apart? That's what the next segment is all about. It describes the common closure principle.
Look at this diagram. It shows the components in a system and the way those components depend upon each other. Let us assume that this component structure is ideal, perfectly designed. Now imagine that a requirement changes or a new requirement is added. How many components will change and be redeployed?
1, my son. Yes, the obvious answer is 1. In a well-designed system, with all else being equal, if the requirements change, just one component should change. Of course, all else is not equal. Our systems are usually composed of layers, like the GUI, the middleware, and the database. When the requirements change, they usually change for all those layers. So the only way to get a single component to change is if a single component contained all those layers. You'd have to mix the GUI, the middleware, and the database together into a single component. And I don't think we want to do that. Decidedly not. Yeah, no. Important safety tip, Egon. Don't cross layers. This actually violates a principle we're going to learn about in an upcoming episode. Components don't cross boundaries. Well, gosh, Uncle Bob, then how many components should change? Well, given that we have multiple layers separated by boundaries, the best outcome is for one component per layer to change when a requirement changes. Is that really possible, Uncle Bob? Can you really just limit your changes to one component per layer? Well, no, not really. And there's lots of reasons why attaining that minimum is difficult. But in fact, you can come pretty close. And that's really the goal of the common closure principle, to minimize the number of components that change when the requirements change. The common closure principle says that the classes we group together into components should be closed against the same kinds of changes. We gather together those classes that change for the same reasons. We separate classes that change for different reasons. That sounds oddly familiar. It should. It's a restatement of the interface segregation principle that we learned about back in episode 9. In that case, we were talking about grouping functions into classes. In this case, we're talking about grouping classes into components. So the common closure principle says that a component should all be made up of classes that change for the same reasons, right? Well, not quite. You need to say it a different way. While it's true that all the classes in a component should change for the same reason, the way you should think about it is that all the classes that change for the same reason should be in the same component. Oh, I get it. We gather up all the classes that change for reason X and we put them in the same component. Within a layer, yes. Given a change to a requirement, we only want one component per layer to change. So why is it called the common closure principle? What is it you mean by closure? I mean closure as in the open-closed principle. All the classes within a component are closed against the same kinds of changes. Okay, that's really strange. In describing this principle, you've mentioned two other principles, the single responsibility principle and the open-closed principle. Yeah, there's an eerie connection between these component principles and the solid principles. I warned you about that in the previous episode, and we'll see even more of it in the upcoming principles. Okay, now let's say that we've got two components, A and B. Component A changes for reason alpha, and component B changes for reason beta. And now let's say that there's another class, and this class changes for both reason alpha and reason beta. Which component should this class go in? Excuse me? A class that changes for more than one reason? Yes, reasons alpha and beta.
A class with more than one reason to change? Ha 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 ha!
Oh, I guess a class with one reason to change is a bad idea.
Yeah, that's a pretty good guess. Actually, such a class would violate the single responsibility principle. A class should have only one reason to change. And that brings up an important point. The common closure principle says that classes that change for the same reason should be grouped together into components. Those reasons are the responsibilities that we learned about back in episode 9 when we studied the single responsibility principle. In episode 9, we learned that a responsibility corresponds to the needs of an actor. So when the common closure principle says that we group together classes that change for the same reasons, it means that those classes all have the same responsibility and all serve the same actor. In other words, the classes within a component are closed to all but their prime responsibility. They are closed to the needs of every other actor. Consider what this means. Each component in a layer serves a particular actor. So when that actor requests a change, only one component per layer will have to be changed. An excellent outcome. When an actor requests a change, we know which components will be affected and which will not. Right. Our goal is to create systems that serve multiple actors. Those systems are composed of architectural layers that separate business rules from details. Those layers are partitioned into components, and each component is composed of classes that serve the actor for that component. The common closure principle describes which classes we put into components to achieve that goal. The third and final principle that we're going to study in this episode is called the common reuse principle. And once again, we're going to see that eerie connection that these component principles have to the original solid principles. Except in this case, that connection will be to the interface segregation principle. So now let's say that you and I are working on a project together. This is your component, Y, for you. And this is my component, I, for me. Your component depends upon my component. So Y depends upon I. Now the reason for that dependency is that there are classes within Y that depend upon a class in I. But there are other classes in I that Y does not depend upon. So now let's say that one of those other classes in component I changes, and that causes component I to be re-released. What should happen to component Y? Nothing. Nothing that component Y depends on is actually changed, so nothing should happen to component Y. Naive. The component Y depends upon the component I. When the version number of component I changes, component Y must be retested and redeployed. Doing otherwise would be negligent. This is a question of process. Components are often built by different teams. When one team releases a new version of a component used by another, the using team's process will almost certainly involve retesting and redeploying all the components that they build that use that newly released component. Now, in small teams, the team members can conspire together to avoid the retest and redeploy of component Y, because they would all just know that the changes to component I had no effect on Y. But in large teams, the situation is different. This information is hidden, and so procedure takes over. Component Y will be retested, will be redeployed, and might even be given a new version number.
And so the owners of component Y are liable to find that they must go through a lot of fuss and bother to recompile, retest, and redeploy their component for no good reason.
Clearly, this isn't ideal. We don't want to create a bunch of busy work for the consumers of our components. So to avoid this, we should limit the constituents of our components to those classes that are used together. This is the common reuse principle, which says that you should group together classes that are used together and separate classes that aren't used together. Or if you'd prefer, construct your components such that when you use a component, you use all of the classes within that component. There's that feeling of familiarity again. I know I've heard that before. Of course you have. It's the interface segregation principle from episode 12. The interface segregation principle told us to avoid creating classes that depend upon methods that they don't call. The common reuse principle tells us to avoid making components that depend on classes they don't use. Or, if you'd rather look at it this way, the interface segregation principle tells us to create classes where if one method is used, they're all used. So, the common reuse principle simply tells us to create components where if one class in the component is used, they're all used. Remember, loose abstractions sink applications. Right, it's all about the problem of too much knowledge. When you use a component that has 10 classes in it, but you only use one of those classes, then a change to the other 9 can still affect you. You know about them. To drive this point home, I feel a story coming on. Do you feel a story coming on? There's a story coming on!
Grandpa, tell the story!
Well, now, let's see. It all began back in 2002. This was back in the days when I was still using a Windows PC. It was running Windows 98. I had the Windows 2000 installation CD for some time. It was sitting on my desk, but I was reluctant to install it because my laptop was working just fine. But then came the fateful night where I finished up some writing at about 11:30. The wife and kids had long since gone to bed, and so I looked around my desk for something small to fill the time. And my eyes spied that Windows 2000 installation CD. And I thought, well, that ought to take about 30 minutes. So I picked up that CD and I shoved it in the slot of my laptop and I started the installation procedure. The installation script used this clever little billboard metaphor. It showed a picture on the screen of you driving down a road, and these billboards would pop up every once in a while. The first billboard came up and said, "Congratulations for installing Windows 2000." And then another billboard popped up and said, "This process should only take about 45 minutes. And then more and more billboards would pop up. And so I started reading some stuff, looking at papers, and every once in a while I would look up to see some more billboards passing by on the screen. Those billboards popped up every couple of minutes. Each one of them told me about some exciting new feature inside of Windows 2000. Oh boy! After about 45 minutes, the final billboard popped up, and it congratulated me for installing Windows 2000 and assured me that everything was going to be fine after the reboot. So then the system shut down and restarted, and it takes about 5 minutes for that restart to finish, and during the whole restart process, everything looked like it was going to be fine, but at the last minute, it crashed. I tried restarting it several more times, and each time it would regale me with 5 more minutes of pleasantries and good indications, and then it would crash. This being Windows circa 2002, I knew what to do. The procedure was to reboot the system into safe mode, where every pixel is the size of a postage stamp. Then, while peering through this hyper-pixelated viewport, you had to go into the control panel and disable the driver that was crashing. The problem was that there were several hundred drivers, and I had no idea which one was causing the problem. So I started a binary search. So first I disabled the top half of the drivers, and then I rebooted it back into normal mode. That took 5 minutes, but that reboot was successful. So the problem must have been in the top half of those drivers. So then I rebooted back into safe mode, which took another 5 minutes or so, and then I disabled the top half of the top half, and repeated the cycle. By 3 a.m, I had finally done 6 more repetitions of this procedure, and I'd isolated the problem to the driver for the voice synthesizer in the modem chip. I don't know why there's a voice synthesizer in the modem chip. I don't know why there's a driver for the voice synthesizer in the modem chip. All I know is that the driver for the voice synthesizer in the modem chip is crashing my system at reboot. That's what happens when you release a component that contains classes that your users don't use or care about. When those classes change or misbehave, your users will be affected. And so we make our components as cohesive as possible. We don't want casual changes to one component to cause huge problems for users who don't care about those problems.
These three principles are not cooperative in nature. On the contrary, they each pull the design of the components into different directions. This can be seen on this tension diagram.
Oh, brother, here he goes again with some highfalutin academic lecture about something so simple my mule could understand it.
Each principle forms a vertex of the triangle, and each edge describes the situations that the opposing principle is trying to avoid. Each component occupies a point within this triangle. The closer it is to a vertex, the more it conforms to the corresponding principle, and the less it experiences the situation on the opposing edge. So, for example, a component that sits here at the release-reuse equivalence principle will be highly reusable. It contains classes that are reused and released together. But also note that a component in this position is very far from the common closure principle and the common reuse principle. This makes sense because the release-reuse equivalence principle tends to add the classes to components, whereas the common reuse and common closure principles tend to limit the number of classes in a component. And this means that a component in this position may cause unnecessary changes to other components in the system and be subject to changes from many different responsibilities. Now, what he means is that if you follow that there reuse-release equivalence principle and only that, well then, you'll sure enough create a nice reusable component, but you'll also load that component up with all kinds of classes. It'll be a pain in the patoot to live with. It'll change for all kinds of reasons, and it'll interfere with all sorts of other components too. Now consider a component that's very close to the common closure principle. This component will only be affected by one responsibility. Changes to other responsibilities will not affect it. On the other hand, it may not have enough classes in it for convenient reuse, and it may have classes in it that other components don't care about. Now, what he's trying to say is that if you concentrate on that there common closure principle, well then you'll sure enough create components that only change for one reason, but they'll also be about as easy to use as a dead porcupine. And all the other components, they'll flail around like possums in heat. The point is that you cannot satisfy all these principles at the same time. You must choose the ones that are important to you and how much to conform to each one. You must choose your position within this triangle.
It turns out that your position within this triangle is a function of how mature your project is. Early in a project, you tend to focus more on the common closure and common reuse principle, so your component tends to be closer to those two vertices. But then as the project matures, it moves more and more towards the release-reuse equivalence principle because the emphasis of the project switches more towards reuse and less towards developability. And what this means is that the component partitioning you choose today will likely not be the component partitioning you wind up with later. Component partitioning depends on project maturity.
Precisely! Reusability and developability are use cases. And as we all know, the architecture of a system should scream about its use cases.
As a project grows in maturity, the reusability use case becomes ever more important, and obviously the architecture of the system must change. Consider, for example, the architecture of java.lang or java.util. These components conform entirely to the release-reuse equivalence principle and pay almost no heed at all to the common reuse principle or the common closure principle. The reason for this is that these components are entirely about reuse. So we've covered a lot of ground here. We've studied the force of cohesion, the force that binds classes into components, and we've studied a variety of false cohesion forces as well. We discovered that the determinant of cohesion is independent deployability. And then we learned about the release-reuse equivalence principle, which told us that in order for a component to be reused, it must also be released. Indeed, the smallest thing that you are willing to release is the smallest thing anyone else will be able to reuse. Or, in other words, the granule of reuse is the granule of release. The common closure principle was next. It states that classes that change for the same reasons belong together in the same component. Classes that change for different reasons should remain separate. And remember, these reasons are the responsibilities from the single responsibility principle.
And then we learned about the common reuse principle, which was like the interface segregation principle because it warned us of the problem of too much knowledge. In particular, it said that when you depend upon a component, you should depend upon all of the classes within that component.
Yeah, and then we learned that real life is about as messy as a donkey giving birth. That there scientific fella put up that triangle of forces and showed us that to try and fit a component into all those principles is about as easy as putting bobcats and chickens into the same corral.
And from that we learned that software architectures change as projects get more mature.
And we learned one other thing, although it was subtle. We learned that systems are made up of layers that are composed of components that contain classes that house functions. And so, for the first time in this series of videos, we've seen the big picture, the 30,000-foot top-down structure of a software system. It is composed of isolated layers, made up of components that are reusable and independently deployable, whose classes are cohesively bound and serve single actors. But lest you think we've passed the pinnacle and reached the culmination of this video series, pay heed as I paraphrase the words of Winston Churchill, for we have not yet come to the beginning of the end. Rather, we may have just approached the end of the beginning.
Yeah, he's right. There's just a whole load more we have to talk about. There's 3 more component principles, principles of cohesion, and then of course there's advanced test-driven development, agile practices, acceptance testing, functional programming, a whole boatload of design patterns. You're not going to want to miss the next exciting episode of Clean Code, episode 17, Component Coupling. Come on, you dogs, let's go. Dogs. Out to walk. Let's go, dogs. Good dog. Good dog.
Stars often come in pairs, and sometimes those pairs can be pretty close to each other. What would happen if a wife dwarf star, the wife of a white dwarf star, a wife dwarf star?
It feels right. Feeling ain't got nothing to do with it.
And I don't remember the rest of the line. And it makes me feel bad. So the first rule of copenint confunction. There it is, copenint confunction. The first rule of copenint confunction. I'm not even sure I want to know what copenint means. That a component la 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 la. Opponent says
Ze pullde ze da, des Gages Kamera Shabam, and so got chichen to bam.
Yeah.
Yeah, something.
Let's see, it's getting dark here. Oh yeah, it's starting to get dark. Well, that's good because you can see my house. Let's go to my house. There's my house way up there.
Oh my. Way up on the mountain.
Fortress on the mountain.
Yeah. Wow, it's all lit up.
Yeah, I got it all lit up and keeps all the bad guys away.
Do you have cats?
Nah, my cat died.
Oh, how did it die?
The creeper blew it up.
Oh. I had a creeper blow me up the other day. Oh, yeah. How'd you do that?
Well, you have to go to the nether.
Fire?
You have to go to the nether and get this stone called netherrack.
Wow.
And netherrack burns forever.
Oh.
So it's kind of like a giant torch.
Oh my goodness. It's a lot of energy getting up to your house. It's a glass house, huh?
Glass and stone. Mm-hmm.
Are those chickens on your stairs?
Yeah, I keep chickens around. Some people think they're spies. I kind of think they're extra food.
Spies.
Yeah, so...
Dirt and what did that say?
Dirt and exotic stone. So in here I've got obsidian, netherrack, a bunch of netherrack actually. Some soul sand, which I don't have any use for. Sandstone, glass panes, glass, junk like that.
We're working hard.
This is